Hello, everyone. This is Chemistry 151, and we're going to get started with Chapter 1, Essential Ideas. Now, I have uploaded a series of PowerPoints. There's something like 84 slides. I'm not going to go through all 84 slides. The way we're going to do this is I'm going to do some PowerPoint slides, and I'm going to make notes on them, important notes. These are things like definitions that you really need to know, and um, maybe a little bit more in depth as to what the slides do. Also, I have what's called a graphical tablet, and I'll be able to use that to open up additional ideas as we go along. Okay, so this is Chemistry 151. This is the textbook, Essential Ideas. There's another one when you try to download it that's called Atoms First. That's not the right textbook. It's the same textbook, but the chapters are not quite in the same order. So first off, we have the outline of the whole chapter. We have some introduction, which is chemistry and context. I won't go through that. Basically, we're going to go right into the chemistry. Phases and classification matters, physical and chemical properties. We'll do that first. I'm going to break these up into separate videos. Okay. And then we'll get into measurements, and which is basically what chemistry is really all about. And we'll do mathematical treatment, a little bit on uncertainty, accuracy versus precision, but mathematical treatments involve what are called significant figures, canceling units, and that sort of thing. And probably 1.6 is probably the part that most people are going to struggle with. We'll spend some time on it as far as that goes. Now, um, chemistry, unlike some other sciences, is actually based on observation and experimentation. In other words, if you can't measure it, it doesn't exist. And so we have things like hypothesis, which just means we're trying to describe what's going on. And then we have a theory. And a theory, all a theory means is that we're pretty sure it's right. It may be wrong, but it's testable. In other words, chemistry is not about opinions or anything. It's either real or it's not. And so now we get into actual chemistry part of this, and that's phases of matter. Now we have three phases of matter: solids, liquids, and gases. Okay. And the textbook actually goes into something called plasma, and I've been asked this many times, is like, well, isn't plasma a state of matter? And it depends on who you talk to. To me, plasma is not really a separate variety. It is more, to me, a kind of gas that happens to be ionized. If you want to see plasma, all you have to do is look inside a fluorescent light bulb, like in a classroom. You know, those big long glass tubes, that actually has plasma in it. It's got electricity that's going through it and excites the different atoms and molecules that are in there, and well, then it glows and you get light. All right. So matter. What is matter? That's anything that has mass, really. And occupies space is maybe a little bit restrictive, but most things that are matter actually occupy space, and it has mass. In other words, you can put it on a scale and you can weigh it. It might not weigh much, but it has some sort of mass. And we use weight and mass kind of interchangeably, but mass is strictly the correct form when we talk about how much matter something has. Weight is how much gravity is pulling on something. So something that weighs like 100 kilograms on Earth, um, if you stick it out in orbit, it would appear to weigh nothing. You know, it's weightless. We're out in orbit, we're out in space, and it seems to be weightless. But if you try to push on it, you quickly discover that even in outer space, things still have mass. It takes energy, it takes effort to move things, even if they're weightless. And that's one of the things about mass. It's there. Now, there are things that exist which don't have mass, and well, you're seeing some right now, which is the very light that's in this room. There are photons, many bazillions of photons, and they don't have mass. They're particles of energy, but they exist and they're there. So there is possible to have things which don't have mass, such as light. Now, the three states of matter are solids, liquids, and gases. Now, when we have solids, liquids, and gases, solids are rigid in the sense of once they form a shape, they stay that shape. So if you can think about, say, a table, and I'm not much of an artist here, but here is, well, I guess you could call that a table. And what shape does it take? Well, it's table shaped, and it's not going to stop being a table just because it's standing there. And so that's what it means to be rigid and have a definite shape. Once you form it up, it's going to stay in that shape and be a definite shape, and it will be rigid. Now, another characteristic of solids is that they can't really be easily compressed, so they're non-compressible. In other words, you can't just take a cylinder of, say, steel or something. You can deform it, you can put a lot of pressure on it and flatten it out, but you're not going to be able to compress it and make it smaller. That's not going to happen. Okay, it's not going to become smaller. Now, a liquid flows, which means that, well, if you take some water in a beaker, it will flow on out and you can put it into another beaker. Now, when we say a solid is rigid, we also mean that if you look at the individual atoms, they're close together. They are close and they don't move. Now, a liquid, on the other hand, the particles are still close, but they're a little bit further apart, typically, just a little bit. But they can flow around each other like that. And so that's the flow that's going on. So they're capable of moving and flowing. That's what makes flowing. And if you have if you say pour water from a beaker to a beaker, if they're different sized beakers, you don't change the volume. If it's 100 milliliters over here, then it's still 100 milliliters over here. And if you pour from, say, a Coke bottle, let's say we pour from a Coke bottle into a glass, it goes from being Coke bottle shaped to being glass shaped. So that's what it means to take the shape of the container, is that whatever you poured into it becomes the shape of whatever that container is. Now, it has the same volume. That's very important. So volume here, same as volume over there. Now, a gas is very different. A gas, the particles are very, very far apart compared to solids and liquids. And they move around randomly, and they're fast. Okay, these gas particles are moving around randomly and very quickly, and they take the shape of the container. So if you take the air in this room, well, the shape of the air in this room is room shaped. And the air up in the corner is the same as the air on the other side of the room. And what's its volume? Well, it's where the volume of the room is. Now, I can take the air in this room, compress it down, and put it in a tire. Same amount of air, except now instead of being the shape and size of the room, I can take that same air and put it into a tire. And that tire is now the air is now the shape of the tire. And it's compressed. Now, solids and liquids and gases can't very well be compressed, but gases can. You can smash them down and make them very small compared to what they started with. You can also expand them out to fill the shape and the volume, whatever the container is. Now, one of the things that we have to know here is that solids and liquids are actually called the condensed phase. And I apologize, I'm using a graphical tablet and my handwriting is not the best in the world, but solids and and this is important, solids and liquids are called the condensed phase because they're condensed in on top of each other, just like over here and just like over here, whereas gas is not a condensed phase. The particles are very far apart. If you want to take it into condensed phase, then you cool it down until it turns into liquid, like liquid nitrogen. You may have seen that in some sort of science demonstration, maybe in middle school or high school. Someone brought in some liquid nitrogen, and you can turn that in, but that's condensed. That's the condensed nitrogen. Now, here's some examples of cartoons of what a solid, liquid, and gas look like. And as you can see, you have the solid, you got a cube of something in there, and you got a liquid. Let's say you're melting, say, solid water and turning it into liquid, and then from the liquid, you can turn that into steam. And the solid chunk of ice is going to stay a cube. And then the liquid water is going to become, well, liquid water. And then when it turns into steam, steam, just like what you see coming off of, say, a spaghetti pot, that steam coming off, it's gas, and it's going to go out into the room and eventually fill up the room with additional water vapor. Now, as I mentioned before, mass is a measure of the amount of matter in an object. And so in outer space, so even at 0 G, zero gravity, still has mass, even in outer space. And if you go to say the moon, things weigh less on the moon, things weigh less on Mars, but it's still the same amount of matter in the sense of no matter where you measure it, either outer space or on Earth, if you have 1 bazillion um, particles of a particular atom, it's going to weigh the same no matter where. It's going to have the same mass no matter where you are, but the weight is going to be different. Okay, it's going to be different. Now, here comes a classification. We have matter. Matter is anything that has mass. Anything that has mass is matter. Now, constant properties of composition is just to decide whether it's a mixture or not. But here's the thing. Pure substance. Let's start with pure substance. That means there's only one thing in there. Only one thing present. Which means it could be gold. It could be a sample of say water. It could be anything. It's just pure substance. Now the thing about a pure substance though is this is only a category. It's never an answer. It is a category. Now, when we have pure substances, though, we can have two sorts of things. Elements, what makes an element is it cannot be broken down. All right. In other words, if it's on the periodic table, then it's an element. And periodic table is actually called the periodic table of elements. Now that's a thing. An element is a thing. A pure substance is a category. It's not a thing. All it means to be a pure substance is there's only one thing present. In other words, it's pure water, pure gold, pure copper, pure oxygen gas. Okay. Now, compound is two or more elements bonded. They have to be bonded. And you can break them down. They can be broken down. Examples of compounds would be, say, like H2O. We can break that down into hydrogen gas and oxygen gas. And if I wanted to balance this, this would be 2 and 2 right there. And we'll get into balancing equations. I'll show you how to do them. And so it's very important to realize pure substances is a category. It's not a thing. It's a category. All it means is you have one compound or one element present. And even pure just depends on who you're talking to. So even, gold usually comes as 99.99% as gold, which is AU on the periodic table, but it's not 100%, but that's pretty pure. But if you're doing something like semiconductor manufacture, maybe that's not pure enough. And that's when we get into something called mixtures. And a mixture means you have more than one thing present. It means we have more than one thing present. And we call that a mixture. And there are two kinds of mixtures we have. And once again, mixture, just like pure substances, is a category. It is a category. It is not a thing. All right. Now, we have two kinds of mixtures. We have homogeneous and we have heterogeneous. Now, homo means same, and hetero means different. Okay, so we have same and different. Now, the best example I can think of homogeneous is air. Now, the very air that you breathe is a homogeneous mixture. It is about 70% nitrogen, about 24% oxygen. It's got some argon, water vapor, and some other things in there. All right. Now, the thing that makes homogeneous is sampling. And can you see? If you look at a sample of air in one corner of the room, it's the same as a sample in another corner of the room. And if you look really close, it just looks like air. All right, you can't tell. Now, heterogeneous would be something like, oh, I don't know, like salt and sand mixed together. You can mix salt and sand, and one of the things about heterogeneous is that you may be able to use fairly simple physical means of separating them, but more importantly, if you look at the salt and sand mixture under a microscope or even just a magnifying glass, you can see the individual particles of sand and you can see the individual particles of salt. You can see them. That's what makes heterogeneous. Soil. If I go out in my yard and take a sample from the front yard and take a sample from the backyard, they will look different. One might have a little bit extra leaves in there, or a little bit extra. Around here, it's mostly sand. It may have a little bit of extra clay in there compared to the other side of the yard. And so, and even if I just look at the soil, if I just pick up a sample of soil and I look at it, you can tell that there's different things in there, and that's what makes it heterogeneous. Okay. Now, if I wanted to separate a heterogeneous mixture, it may be pretty simple. How do you think, we could separate salt and sand? And by the way, one of our labs is going to be separating salt from sand. And that would be, you could take that salt sand mixture and mix it with some hot water, and the salt will dissolve, and then you pour off or decant the salt water off of the sand. If you dissolve it in water, we got salt water, and then you can dry them both, and you end up with dry sand and dry salt. And so heterogeneous mixtures can be very easily separated. Homogeneous mixtures can be separated, but they typically require a little bit more work. There are means, like if I wanted to separate the nitrogen from the oxygen and air, one way to do that would be to cool down air. If you cool it down and put enough pressure on it, the nitrogen will come out as a liquid, and so will the oxygen, and so will the argon. They'll all come out and separate out at different temperatures. So that's one way you can separate out different sorts of mixtures. But the bottom line is when you have a mixture, it's more than one thing in there. Now, one thing you have to be careful about, some caution here, is that if you see something like this, that's glucose, by the way, then you have to be careful. This is more than one element, but it's part of a compound. And so that makes it a compound. It's not a mixture. A mixture would be like salt and sand, which would be sodium chloride plus silicon dioxide. That's salt and sand. That's two different things. Okay? That's two different things that we can separate out in some sort of way. That would make that a mixture. Okay? So be very careful when you're talking about mixtures and pure substances. Those are categories. And an element, well, how do you know it's an element? Well, it's on the periodic table, and it's the only one in there. That makes it a pure substance. And a compound will have some sort of formula, like glucose over here. That has a formula, C6H12O6. All right, physical and chemical properties. All right, physical property is anything that you can test without changing what it is. Okay, so like color, for instance. If I look at a copper penny, it's copper colored. And this may seem silly, but just the act of looking at you have to look at it to be able to tell what the color is, but looking at the penny doesn't change what the color is. Same thing with melting. If I melt ice or if I boil water, it's still water after I'm done. It may be solid water, otherwise known as ice. It might be liquid water, otherwise known as water, or it might be boiled water, otherwise known as steam, but it's still water. Okay, and the only way we can tell these things is by doing a measurement, such as, heating it up until it melts. Well, that's a measurement, but we're not changing what it is. Okay. Now, physical change is that change. It doesn't cause the thing to be different. Now, that would be like, also think about this. If I rip up paper, if I put paper through a shredder, it's still paper. It's shredded paper, but it's still paper. Okay. Now, here's some examples. Melting butter. As long as you don't burn the butter, it's a physical change. And vaporizing water. All right. Now, chemical properties, on the other hand, to determine a chemical property, it is going to change into something else. Flammability, for instance. If we have paper and we burn it, it's going to turn into CO2 plus water plus ash if I burn it. If you burn a paper, you're determining whether it's flammable or not. And it's not paper anymore after you're done with it. Okay. Acidity. The way you determine acidity is how much does it react with, say, a base. Here's acidity. That's an acid. That's a base. Okay. And so, to find out the chemical properties, you have to do something to it. to determine corrosive, whether something's corrosive or not. But by the way, whether something's corrosive or not has to do with whether it can pit metal. Well, how in the world are you going to find out whether it pits metal without doing the reaction? And so when you do uh, measurements of corrosion, then sure enough, you're going to change what's going on. You're going to have a piece of metal that's nice, smooth, and shiny, and then a piece of metal which is not. That's what corrosion is all about. Okay, here's some examples. If you look on your left-hand side, you'll see, here's some sample of iron that has rusted. That is a chemical property. It's not iron anymore. It's actually iron oxide. And then you have what I presume is a side of a motorcycle, and it's got chrome on it, and chrome doesn't corrode, which is a chemical property. Now, you can get it to corrode, but it doesn't corrode as easily as, say, bare metal, which is the whole point of putting chrome on different things. Okay, and here's some examples of some chemical reactions going on. Copper and nitric acid forming copper nitrate and nitrogen dioxide. We have a burning match. We have and C, cooking, and D, with a banana. And here's a pro tip: anything having to do with food is a chemical reaction or a chemical property. So digesting a meal, definitely chemical. Cooking, definitely chemical. You may not realize this, that every time you cooked something, it was a chemical reaction that you were doing. All right. Now, finally, we have what are called extensive and intensive. Extensive, think about what's X means, like on the outside. Intensive means on the inside. All right. So extensive means it depends on the extent of how much stuff you have. So my weight, when I measure myself in the morning, is an extensive property. It changes. It depends on how much I have of me. That's an extensive property. Um, but my temperature, which is uh, how much my blood is, how much my temperature of my body is, that does not depend on how much of me that I have here. Um, so if I'm 97.8, then I'm 97.8 regardless of whether I weigh 180 or 200 pounds. I'm still 97.8. But the amount of heat that I have depends upon how much stuff I have. And so um, heat is a measure of energy. And so that's an extensive property. So, how would that look? Like, the following are extensive properties, and you've got, like, I don't know, mass, volume, heat, energy. These are extensive. Um, Intensive, you got density, temperature. Density, by the way, is intensive because it is grams per milliliter, and it doesn't matter whether you take a 1 milliliter sample or a 10 milliliter sample, you get more and more mass to go along with it. So that's what density is, an intensive property. But other intensive properties would be like, say, the color of that penny. It's kind of a reddish brown from the copper. And it doesn't matter how many pennies you have. If they're new, at least, then they'll all be the same color. Um, and it doesn't matter, how much air you have, it's still colorless. The density is the same, whether you're one part of the room or the other. And so it's an important distinction between the two: extensive properties and intensive properties. It's a definition, much like the classification of matter was a definitions, and solid, liquid, gases, those were definitions. So the first part of what we do in chemistry here is we just kind of go through some definitions. So that's what we're trying to accomplish here.